This whole unit really has been about how do we know what we know. And there's two types of thinking that we've discussed, and that's our common everyday thinking, the kind of thinking that we all do, that we must do. And if we don't do this kind of, if we try to do scientific thinking all the time and try to test everything, it would just be all consuming. So this is, although necessary, has some flaws. And when we look at scientific thinking, we know that scientific thinking helps us deal with a lot of issues that we find in our everyday thinking. And I say our because everybody thinks this way. This is not a necessarily a bad way of thinking. As I said, it's necessary. However, when it comes to things that are fundamental, and when it comes to ideas that either we find interesting or that we find necessary to know, to be closer to the truth, then scientific thinking is going to be necessary in order to accomplish that goal of getting closer to what is really going on. And so the two work in tandem because we're human beings. But in scientific thinking, we we have certain rules that we have to learn, and we have to be able to abide by in order to keep uh, the validity of what we're saying. So this questioning of what we know and what we don't know is not new. It started long ago, and Thomas Jefferson has a famous quote where he says, "He who knows nothing is closer to the truth than he whose mind is filled with falsehoods and errors." And that's the it sounds beautiful. The real question, though, for Tom, what would have been, how do you know what the falsehoods are? How do you know what the errors are, and how do you measure that, and then how do you compensate for that? Remember that everything that you know. This is your existence. You can't change uh, your perception without some effort. And so this is not something that we're all used to in a movie or in a show where we see the truth in the murder mystery and we're wondering why the murderer is getting away with all these things. The murderer is getting away with all these things because the victim is in the movie and doesn't see what you see. So we're used to watching television and videos and where we are the third person, and we get very confident as a third person, as an observer, that what's going on is we know so much. But when you're in the middle of the experience and you have limited perception and limited viewpoints, then it's much harder to tell where is this error versus where's the truth. So this error and being able to tell the difference between the fact and of what's going on and the level of error that we're making is not that easy. A really quick kind of fun example of what I'm talking about is you can take a look at this picture, and a lot of people will see one thing and others will see another. And this is common. You've known these, you've seen these at various stages in your experience, probably in books or at museums, and you can see that this can, to some people it looks like a skull, and to others, depending on the aspect, the viewpoint, it looks like little dragons and wind blowing on a ship and people up on a mast. So different perspectives, different viewpoints, different experiences. Even what we see and hear and smell can be influenced by our environment. So all this, and there's whole hundreds of years of philosophy, of thinking, of reasoning that led to this understanding of what is scientific thinking. And a lot of it is going to be just compiled into this short video and what we've covered over this week. The key to the your exam, the key to understanding how to do well all year and do anything in science is how do we know what we know, and what is the procedure, what are the components of that thinking, and let's go ahead and take a look at that a little bit. So we went through the history of science. I'm not going to rehash this. We've covered it in class. It's here in front of you. And we looked at kind of the big difference between ancient science, ancient thinking, and modern science. And the big thing, there was a couple big things, is first, they focused on why. Why was a big question for the Greek philosophers and for the ancient Egyptians and any ancient ancestors, including the Mayans and the Aztecs. They accomplished amazing feats of technology and science. The issue they had, and maybe it's not an issue, but the focus they had is they focused on why, and because they focused on why, it led them down thought pathways that really did not accomplish everything they could have in the amount of time that they had to work with. Remember, we all have limited time on this earth, and we need to build on each other's work and communicate with each other. And that was another limitation, of course, that they really didn't communicate with each other as well as they could have. I mean, they had, messengers on horseback and things written down on paper or papyrus. So it's not something, and in the case of the Egyptians, they were secret. They kept their ideas and concepts secrets, where the Greeks were more open about it. The Library of Alexandria, for instance, was burned down. So you have to kind of consider that what the pre-modern science concepts were trying to figure out why. Their focus was not trying to figure out how to do something. And in modern science, we try to focus on how. Of course, we try to figure out why. We see something, we'll ask the question, why did that happen? But ultimately, when you ask that question, it's going to come down in modern science to how does that happen? How did we get blank? So remember that. All right, moving forward. Decision making. This is a pretty simple, straightforward decision making 5-step process that most of us that want to make rational decisions, especially big decisions, want to do. We don't do this kind of decision making when we're trying to choose, let's say, a hot dog, but we might do this kind of decision making when we want to choose what kind of meals do I normally want to eat. What is going to be my dietary strategy, and so on big decisions, on broad decisions, we're going to try to make this kind of logical choice if you are a rational a person who wants to maximize your chances of doing of choosing the best making the best choice. So we first formulate clear statement and issue. And then, so first we have to understand what kind of question do you have? What's your problem? A lot of times we try to answer or solve problems and we really don't understand what it is that we're trying to solve. So clearly describe the problem in as simple a statement as you can. The reason I'm making this, I just want to take a second to say the reason we went over decision making is because in decision making, from this is rooted the scientific method. So making lists and logical decisions, the scientific method is pretty clearly rooted in sound rational thinking. So you want to define the question or the problem. Then you want to gather scientific evidence related to the issue. So you want to find facts. You want to find things that have been tested. And the key is scientific information. There's all kinds of information out there, all right? There's all kinds of information out there that's based in, your problem with, there's a problem with saying scientific method too, scientific information. There is an issue. And the issue is that it's been co-opted by so many different organizations. And so when companies are out there telling you that, Gerbagana herb is going to cure cancer for you. They're trying to make money, and they're going to use some false scientific information. They're going to make it look like scientific information. And so you're going to, one of the problems with finding scientific information, and we'll talk about later, is trying to look at the source. And a lot of you have already had some experience with that when you've written papers or had to do research or something. So the source of the scientific information is important. Who funds the scientist? Does the scientist have a good reputation? And is the publication reviewed by other scientific peers? So you when you're trying to make sure that the information you're getting is as sound and as valid as you can possibly make it, you want a good source. That when you want that experiment to have been looked at by other scientists to make sure that there's no major mistakes, or even we all know that there's errors, but that the errors have been accounted for. So next is list all the alternative courses of action. So you want to make sure that you have all the various ways, directions you can make that decision. Often we limit our decisions to one or two decisions when actually there's many other choices that we just maybe haven't looked at. Then we predict positive and negative consequences. And they say, well, if I make choice A, what are kind of the things that are going to happen that would make me want to make that choice? And then what kind of bad things might happen if I make that choice? So you're kind of trying to estimate the result of that, the consequence of that action. And of course, you have to really focus. Another thing you have to focus on is what's the probability of the negative and the positive. So when you're sitting there, not just saying, well, there'll be this positive thing might happen, that negative thing might happen. What's the probability of a negative or positive thing happening? There's a lot of choices in which we need to, really make this kind of decision making or conduct this kind of decision making. And one of these might be, do I just going to use the scholastic one? Do I study or do I go to the party? And the negative consequences of going to the party versus studying, and you'd list them. Then you do the positive consequences of going to the party, and you'd list them. And what's the probability of the positive happening? What's the probability of the negative happening? And then you have to weigh your alternatives. All right, so you have to say, well, and by weighing the alternatives, what do we mean by that? You have to give value to what you're saying is a positive and negative. So you have to give value to it. So if I really highly value my social structure, my social position in the particular community, then maybe the party is really important to me. However, if I really am concerned about my own future and my ability to be successful in that future, then maybe studying is important to me. However, there may be more than one option. Maybe I can go to the party for an hour and then go back and study, or maybe I can study before I go to the party and go there late. So there's other options that might be available if you put some thought into it. But the other thing that's not listed here is that's follow through. So you have to follow through with whatever decision you make. Otherwise, you're not sure if it was the decision or was it your lack of follow through. So in this diagram, what we focused in on, and you have a copy of it, and we went over it in class, and that's that we, in everyday thinking, we're focusing on trying to find a fulfilled life. We're trying to find the essentials for just living and being happy. In our Declaration of Independence in America, we have, we have the right to pursue happiness. So this pursuing of happiness is a really big deal for us, and it's a big deal for every human being. You want to be to live a fulfilled life. You don't want to end up leaving this earth and just feel like you haven't been able to do much of anything. And in fact, this is one of the saddest things that we see as human beings is when a child passes away, because it's ability to to pursue happiness, its ability to live a fulfilled life, was, cut short. So when we look at the kind of qualities of what it takes to do this kind of happiness thinking, it has these kinds of qualities for each of these categories, and I'm not going to go into each one. I already have in class. But it's important that you understand that these qualities fundamentally have some major differences with these qualities, and you can compare them clearly. And one of the assignments was to see if there's any similarities, and there are similarities. I mean, the obvious similarities are that you have the categories. You still have to do the basic function. You still have to do validity, but the question is, how do you find validity in science versus finding validity in everyday thinking? And what we find in everyday thinking is that our requirement for strict validity, strict analysis of error, our requirement for finding knowledge, looking at sources, this kind of process is limited here in this kind of everyday thinking. And that's because you can't really, as a human being, test all the millions of decisions that you have to make every day, or thousands, probably not millions. When you're deciding, what clothes to wear, what clothes to buy, who to buy them from, these are decisions that you generally are not going to have time to break down the way you need to break down in using scientific thinking. Now, that's not to say you can't sit down on a Saturday and do some research and find out what kind of, what policies a particular clothes manufacturer has, and look and see if the clothes are safe for your kid, or look to see if the clothes manufacturer is using child labor to produce them. Do they give their workers a living wage? What kind of benefits and what kind of pluses and minuses you have. So it's not to say you can't use that decision-making chart we discussed a minute ago to make kind of grand decisions and policies and strategies, but you're not every day going to sit there and do that decision-making chart and pull out your piece of paper and a pen and list the pluses and minuses for every decision you have to make. So everyday thinking is not as stringent as scientific thinking. All right, so that was the point there. An example of everyday thinking that does kind of impact, and there's some crossover, there's some overlap, and there's some really extremes. And this is, of course, is an extreme, and the extreme is that when we don't check for errors, when we don't check for sources, when we don't use logic to make decisions, when our premises are wrong because we haven't checked our facts, then we end up with these very, very serious mistakes in our thinking that end up really impacting a lot and impacting others as well. Crop circles, and they, I don't remember when they first appeared, but I remember them coming out when I was a kid. Crop circles were first. I think they were first time they saw them was in England, and what's interesting is that they have these really amazing patterns, and people were like, well, how did they do that? And it must be obviously an alien ship landing at first, and somebody else said, well, it's not an alien ship landing, it's a message from the universe. And so people are out there thinking that these crop circles were created by some bigger, better version of intelligent life, when really the crop circles were created by hoaxsters, by people that clearly chose to try to trick people. And they admitted to trying to trick people. And not only even after they admitted it, the people still argue. They still won't accept the fact that there was a hoax, even though the people that created them said they were. These people feel that there's some kind of supernatural event, anyways. And see, that the reason why this is the case is back to how we use it, how common everyday thinking works. And So once you've committed to an idea, it's difficult to change. It's difficult to change because we've invested energy and concept, and we've connected and made gave this idea a lot of value, and so now it's difficult to take that idea and then change it and say, okay, that idea was wrong. Let me find another idea. And there's no real official accepted way of dealing with error in everyday thinking. You have this error, it exists, you kind of accept it and you kind of just move on. It's just an exception. As you move on, as if the error were an exception in your life, you move on as if that's just an ambiguous point that you're really never going to know. There's no way of knowing it. So that's what you do when you are confronted in everyday thinking. This is what we've been trained to do by life, is when you come up to a problem in your thinking, when there's an error, how do you deal with that error? You just kind of sweep it under the rug. You just accept it as something that's unknowable, or you accept it as something that is that's something that somebody else is wrong, or that there will come a time when people will understand. Whatever it is, crop circles is just the example of it, but whatever it is, the thinking, the type of thinking that leads to this error, this major conceptual error, it doesn't allow for error correction, no formal error correction. And because there's no formal error correction, and there's no check to make sure your premises are correct, people continue to make the same mistake, and they continue to believe in the oddest things. And there's just thousands and thousands of examples of it. It's not to say that they might be right. There may be some alien race who's leaving messages for us, and the government is covering it up. That might be happening. However, when you really start to do the kind of decision making we talked about earlier, and you start to say, well, what's the probability that that's happening versus the probability that this is a hoax, especially when we have hoaxers coming out and saying that they did it. What's the likelihood of this happening? Once you start using that kind of rational thinking to make decisions, it's much more difficult to accept this idea that crop circles are messages from the universe. And so it gives you an option to deal with error and to deal with misinformation. Okay, so deductive reasoning is something that we use in science, and we also use inductive reasoning. So we use these two types of reasoning. Inductive reasoning is where you have a bunch of facts or ideas, and you come up with a general principle that explains it. All right, and you say, well, this is the general principle, and we'll talk about this in the next few moments. Is from the general principle, then we're going to, in science, that's, first of all, I want to say that's inductive reasoning. Then in science, what we do is we test that, and we try to see what we can know. In deductive reasoning, and that's what we're going to talk about in the next couple slides, works hand in hand with that, and we have to do both. And when we're talking about doing an experiment and kind of figuring out what we know, what we don't know, is deductive reasoning. We have to take the general principle. So that's where we have the general principle. And we instead apply the general principle into the tests. So they both go into this test, and this thing called an experiment, and we use both kinds of thinking to solve a problem, to come up with the most valid answer that we can come up with. So the rules for deductive reasoning, though, there's an error. Often people will say something that sounds logical, and it's wrong. A lot of you have mentioned it in class. The examples that you know of. So when you're talking about deductive reasoning and you're asking yourself, well, how can deductive reasoning, if it's such a good way of thinking, how does deductive reasoning lead us to issues? How can it be wrong? Well, in science, it's not just deductive reasoning. Deductive reasoning just needs A to be true and then B to be true, and then that somehow leads to you to accept. And this little triangle means therefore. Therefore, C is true, and that's really the only thing deductive reasoning does. It says if we accept these two premises, if these two premises are correct, then then our conclusion is correct. And see, a lot of people do solid, simple, really well done deductive reasoning, and they're often wrong because what they do is they've accepted premises that are not necessarily true. And so, this is the hard part. This is the work where it takes work. I mean, it can be all difficult, but it's the difficult part is trying to figure out what's true and what isn't. The politics that's going on this year in 2016-17 for the presidential election in the United States is a really big example of what is the difficulty trying to figure out what is true, what isn't, and especially when there's so much falsehood being proposed as a premise, as a truth. And if you can, and the idea that the politicians are taking advantage of is that if they can get people to accept the premises as true, then the conclusion is they hope and they know that people will make logical conclusions, and the logical conclusion, as far as they can see, is true. And then they hope that once people realize it's true, that they're going to use their common everyday thinking that we use all the time to just not check the validity and not look for errors. And so that's the hope that politicians. That's what politicians abuse in order to get people to believe things that just simply against their own way of thinking, against their own good often. So in any case, I hate to bring up politics, but it's a good example, and I think it's a learning opportunity for us to, when we're looking at things that we wonder are they true or not. It's key that you verify that the premises that not often they'll it's not this. This can follow from A and B, so therefore C is true if A and B are true, but it's A and B. When A and B is false, then your acceptance of C as being true is a mistake. All right. So science, in contrast, what we do in science is we require not only that the logical reasoning be correct, but that our premises be correct. And that's harder than you might think. So making sure the premises are correct is a lot of work. And I guess one of the reasons people just don't do that, and they just kind of accept the premises being proposed, especially if it's associated with their own experience, and they then can just clearly accept the truth of the statement. All right, so let's go on and look at how deductive reasoning can go. Let's look at an actual example. So deductive reasoning, going from premise A. I mean, this is something that a lot of us learned in algebra and geometry. A straight line is the shortest distance between 2 points. This is Euclidean geometry. And premise B is that a straight line from A to B is the shortest distance. All right, from A to B, and then therefore A to B is a straight line. Seems reasonable, and it certainly is. It is logically sound. So it's a logically sound argument. So it's logically sound. Now in science, and of course in math as well, when a math teacher teaches you this, they're talking about a flat plane, right? A two-dimensional plane. But in science and then later in non-Euclidean geometry, when you're looking at, from A to B, this is true. if this is A and this is B, then it is the shortest distance between the two. That's correct. However, if it's a sphere, if it's three-dimensional, well, let's not use a sphere because I'm afraid that it might be difficult to see on this two-dimensional surface. So let's go ahead and use a cube. If we're talking about a cube, you have A on this side, all right? And on the other side, you have, I'll write it real small over here. On the other side, on that side of the cube, is B, is point B. All right? If you cannot get through the cube, if going through the cube, if it's a solid cube, right? So you can't get through it. If that's your path, then going through the shortest distance from A to B is not a straight line, because if I tell you that the shortest distance is going up here on this surface, then moving up across here on this surface, then moving over here to this surface, actually a curved line, so it actually ends up being kind of a curved path, then a straight line is not the shortest distance, because the shortest straight line would be from here kind of straight through, right? So in this case, in the case of a cube, it's not that simple. In the case of a sphere, I'll go ahead and use a sphere, and hopefully you can see what I'm saying. If this is the Earth, let's say, and you're in China on the other side, I'll just put an arrow, that's your B, and over here, A is where we are, and that you ask yourself, what's the shortest distance, how do I travel there? From A to B is actually a curved line all the way around the Earth, so it's not a straight line. Now here is a clear example where in one situation it's true, in a two-dimensional situation this statement's true, in a different situation this is false. So this is true, the statement's true and logically sound, and on a curved surface it's false and logically sound. So even though it's logically sound, the conclusion's false. And why is it false? Because the shortest distance between 2 points is not a straight line on a curved surface on something like the Earth. So this is the problem in the statement, in this logic, in this sequence of knowing. In one situation it can be true, in another false. So we have to be careful when we're applying kind of our logic and we're doing deductive reasoning. We have to make sure that these premises are correct. Now let's go ahead and take a look at something else. Here's a really extreme example. And by the way, I find that this happens a lot among all of us, among adults and children. And one of the things you have to remember is, again, back to what I said earlier, which is the premise. Make sure your premises are correct, and therefore your conclusion has the best likelihood of being right. So in the case of what went wrong, what's wrong here, let's take a look at it. And it says humans are the only tool-making organisms, and then it says, wow, well, woodpecker finch uses tools. Then of the logical person that doesn't really check for answers, as we said in the way we normally use our thinking, the way we normally think, we don't check for our answers. If A is true, the humans are tool-making organisms, and B, that the woodpecker finch uses tools, then our conclusion has to be, therefore, the woodpecker finch is a human being. I mean, it's just one thing follows the other. Is it logically? Logic is correct, right? The logic of this is almost undeniable. If this is true and this is true, then this is true. And that's just really simple. It's really straightforward. What's the problem? I mean, obviously the problem is that, at least I think it's obvious, is that humans are not the only tool-making humans are not the only tool-making group. That it is obviously other organisms do it too. And these finches are just an example are just one of the many animals that do create and use tools. So the logic is correct, but the premise is wrong. And it's wrong, and this conclusion will be wrong in every situation because the premise is fundamentally wrong. Where in the previous example, the error, the premise was wrong only in non-two-dimensional systems, so only on paper was the premise right. Everywhere else, or on paper, on a board, or any length and width. So two dimensions. Let me say that two dimensions means length and width. So anything with area, you'll notice there's no depth, right? And you all know what 3D is. At least most of you have gone to movies that are three-dimensional. There's length and width, and then there's also depth. So when you're talking about 3 dimensions versus 2 dimensions, in 2 dimensions the previous premise was correct. In 3 dimensions it was wrong. In this case, it's wrong in any situation because this premise here is absolutely wrong. All right, so deductive reasoning can lead us to issues and can lead us to problems, especially if we don't check those premises. So the scientific method is listed here. I'm not going to read it to you. I'm sure you at this point you realize what it is. You can read it for yourself. You should have taken notes on the PowerPoint yourself, and of course we've used it in the classroom. So scientific method is kind of straightforward. One of the things I do want to go over though are kind of the different parts. And I wanted to go over this because so many of you had issues with your first lab report, and I haven't finished grading them, but I'll get on that right after I'm done with this video. When we're looking at the scientific method, kind of some really basic concepts, is obviously the hypothesis. And the hypothesis has two qualities. First, that you need to make sure you have in a hypothesis. And first, I think and foremost, is it's based on the observations, right? And this is kind of the inductive piece. So you want to have sound inductive reasoning, and you want to make sure that you're basing your hypothesis on what you've seen, and you're coming up with a generalization that you're going to be able to test. And second thing is it has to be disprovable. And to my estimation, this is an idea that a lot of people had problems with, and that means that you have to be able to show that it's false. So that's what disprovable means. The problem in science that we have, as far as logic is concerned, is that there is no way to prove anything. All right, it's just that simple. We can't prove anything. So a quick example would be if I take and I say every time I throw something up, it comes down. Well, how many times do I have to do that before I can say this has been proven? Well, it would have to be done for infinity. I'd have to do it forever to be able to prove that every time I throw it up, it comes down, that there's not one exception, all right, on the surface of the earth, that so not one time did that thing just keep going up. So, but the next question is, how many times do I have to throw something up and it keep going up for this to be disproven? One time. And you see why it's so easy to do this versus trying to do this. It's too difficult to do it for infinity. It's not feasible. So what we end up doing is we end up looking at when we're talking about science, we're looking at things that we can disprove, things that we can say, hey, the evidence here shows that this is not correct. That is a much easier thing to do. Proving things beyond a shadow of a doubt is, well, just impossible, really. So there you have hypothesis. The next thing you have to think about is independent. Oh, let's talk about control groups. You have to define a control group. And what does a control group mean? You have to have a bunch of different test groups. So you have, here's a group here, group one, and then you have group two. So your control groups are going to be tested in different situations. So the first you're going to do your test. Let's say you say, I'm going to use a real simple example. Water, you're trying to say that water is necessary for life. All right. Let's say you say that water is necessary for life. And in group, and we're specifically going to be talking about plants. Okay, let's say that water is necessary for plants to grow. All right, so you're looking at water is necessary for plants to grow. So the obvious thing is to take and plant seeds, right? And in one group, you just don't. What if you just plant the seeds and you water them and they grow? So you add water plus H2O, and you get your growth happening. So are we happy then? Are we done? We added water and the plants grew and the plants seem happy, so that's it. Water is necessary to grow. Well, no, we can't say that because we don't have an example that we can compare this to. We need an example that we can compare this to. So what might we do with the second group? Well, we might, and again, a very simple example. This is the plus water. In the second group, this is group one. In group two, we might take and add no water. Add absolutely no water to it. So if we had no water, and the things grew, then we know that we might be thinking, well, maybe water isn't necessary. But if the things didn't grow and there's no water, then we know that water is not necessary for the thing to grow. So this is where we look at disprovability, and it's control groups that allow us to say, okay, we need to be able to compare. This is your control. And why is it your control? Because you're using it to compare. And you can have all kinds of negatives, all kinds of control groups. In this case, this is going to be your negative control because you expect your hypothesis, which is water is necessary for life to grow. You expect, due to your hypothesis, you expect no growth here. You expect your hypothesis to be, if your hypothesis is correct, your negative control is going to mean that whatever you expect to happen won't happen in two, right? In group one, you expect it to happen. In group two, you don't expect it to happen. And maybe this is a new seed. Maybe this seed, instead of life, maybe is specifically a new seed. And you think that this seed may absolutely need water, but other seeds might not, or you know that other seeds do, but you're wondering if this one does need water to grow. For some reason you think this new seed will not need it, so you put the negative. Make this statement, or you don't know if this new seed needs water to grow. So you might have a different seed, a seed that you already know grows in water. All right, planted. You might go ahead and add water. And these seeds grow. And these seeds growing, though, you knew they would grow because you knew them, you created, you planted them in. They weren't unknowns. This was your unknown. Well, this would be your positive control, right? So this is the control that you know that you expect it to happen. And if it doesn't happen here, then why do we have this? If we knew it was going to grow anyways, why do we have it? Right? I mean, why do an experiment with something that we already know it's going to work? Why would we bother doing it? And the answer is really really important, and that's that this control group, this positive control, even though we know it should work, if something doesn't grow here, then it's something else is happening. For instance, if our unknowns, we added water and they didn't grow, we might be confused about that. If we didn't already know that there's something, if we didn't have a positive control that we could compare it to and make sure that the soil, the light, the air, was all the other conditions that we weren't discussing were actually valid, or were in the right range for these plants to grow. So control groups, positive and negative controls, really do help us in defining what's actually happening, in trying to decipher from observations what we actually know, and what we are only guessing. Now, another thing to point out is that the concept in science of controlling all your variables is extremely important. Notice that only one thing changed in all three groups. Okay, in all three groups, only one thing changed, and that's whether I added water or not. The soil, the size of the box, the number of seeds, the light, the position of the box, the timing of the lights, everything else that I can think of as a scientist when I'm looking at just how does water affect growth. I'm controlling everything else, and this controlling all variables, and this is what we call the controlled experiment, and we're controlling the variables. We just want to make sure that all the other parts of the experiment are not going to change our results. That there's something that we don't know, that we haven't, that some association, some influence that we weren't aware of, that's impacting our results. Right? We call these confounding factors, and we want to make sure that confounding means confused, right? So confounding factors confuse the results. All right. So we want to make sure we get rid of those confounding factors. So we standardize everything. Everything in the experiment is the same except for the one thing we're changing. So if there's a difference in how they grow, then we know it was that one thing that we changed. All right, let's go on. So the scientific method versus non-science, it's really kind of question. I think we spent a good amount of time here looking at this pathway here, and I think that's enough. I think we know. I hope you know already what non-science looks like, what deductive reasoning looks like, and what bad deductive reasoning looks like. On the quiz on Monday, on Tuesday for a lot of you, on the quiz on Tuesday, what you're going to look at is you're going to see passages that you're going to have to define whether it's scientific thinking or non-scientific thinking, and whether this statement is deductively sound or not deductively sound. When you're looking at science, though, and we'll be talking about this throughout the year, and what do you need to know for the quiz, you should be familiar with this diagram. All right. So when you're looking to open the number one thing that you need to know, and by the way, this summarizes a lot of the ideas we've talked about thus far. The number one thing you need to know for the quiz is that in order for it to be scientific, you must be able to disprove it. If you can't disprove it, it's not scientific. It doesn't mean it's not right or wrong. No value judgment is being given. It's just not science. So being able to disprove something is what makes it science. Science is, there's kind of two ways things happen. You have inductive reasoning. So you have these facts, these bunch of facts that you're looking at, and you're trying to find some common general principle that explains it. Plants need water to grow, kind of concept. Or you might just happen upon it. Maybe there's an insight, or there's just an epiphany, or some kind of accident that happens, and you come across this general principle that you want to try to investigate. Either way, you end up with a general principle. In inductive reasoning, you're kind of used to you're used to it. You make some observations, you do create a hypothesis, then you test that then you design an experiment to test that hypothesis with control groups and experimental groups, and you control all the variables, and you collect the data, and you analyze the data, and you come up with a conclusion. In fact, you did that in the lab report that you turned in to me. So that's kind of what you did. When you were talking about creative ideas, you have this insight, and then something happens. You come up with some creative ideas, but in any case, however you end up with getting where you got to go, or however you come to it, the next step is formulating the hypothesis. You have to develop an if-then statement that's disprovable. Again, the whole point, just because it's disprovable doesn't mean it will be disproved. It could be that you collect evidence that supports it rather than disproves it. That's fine. It's just the idea that it has to be able to be disproved. All right. So a good, clear example of that would be, aliens seeded DNA in volcanoes that created humans. That's not something that we can disprove in an experiment. Not to say whether it's true or false. It's just not. It's not experimentally achievable, and so you can't have control groups. You can't control the variables. You can't. You can look at some. There's other evidence that you can look at that might help you collect evidence, but it's just not an experiment that we can do that we can clearly identify as disprovable. So the next thing is design a test that's going to test that hypothesis. And so remember your experience from this lab report that you completed. Your hypothesis should be clear, it should be short, it should be specific. If you try to make it too broad or try to answer the question too broad away, you're losing your focus. It's not science. You're being lazy. You have to make sure that you're clear and concise, and you do the small tests that add up to the big understanding. And design tests for hypothesis. Okay. Then the next thing is you develop a sampling scheme to gather the data. So now you have your hypothesis. Now you come up with a way to collect that data, to do the experiment, collect the data. Then you go ahead and test the hypothesis. And if your data supports the hypothesis, then is consistent with the hypothesis, you just go ahead and keep collecting new data that continues to support it. Remember, we have to repeat. It has to be reproducible. And that's where that word reproducible comes into play. It has to be reproducible. We have to be able to if we can't reproduce your experiment, your results, then it's not science. So to say that I'm the only person that can see the spirit, and it's telling me that you need to give me all your money, or that you need to donate your money to whatever. It's not to say that's not happening, but it's not science. Why is it not science? Because it's not reproducible. You're the only person that can see it. I can't see it. So if I can't see it and I can't test it, then it's not science. And that's the difference between science and some of the other ways of thinking. It's one of the major differences. Now, if you disprove it, then now you have to go. You don't just go back and retest the way you see here. You have to come all the way. You have to go all the way back to the beginning, and formulate a new hypothesis, which is fine. This is actually something that the scientists get just as excited about as this, I think. And the reason is that this leads to new discoveries. this leads to people coming up with getting Nobel Prizes. The fact that, well, they both do, but the idea of disproving a hypothesis means that you have to come up with something new, and this can mean something that's innovative and something that gets you noticed as a scientist and your abilities recognized. So some people are really excited over this, but disproving a hypothesis or finding that your hypothesis was wrong is equal as important if as finding information that supports your hypothesis. Okay, so there's everyday thinking versus scientific thinking. This is a nice graphic. Okay, so when we're looking at scientific knowledge, it's tested, it's generally agreed upon. So you have to understand that everybody does an experiment, and once you do an experiment, if somebody says, well, okay, I did the experiment, we got this data, we have these results, then obvious. I think it's obvious that we all are going to agree with it until somebody finds something that disproves it, and that's the key. Is that I say this is true, this is my data, it's true. So if you disagree, find some data, do an experiment that tests it, that shows that my idea is wrong. Until then, my idea stands, and that's really the fundamental core philosophy of science. In the frontiers of science and advancing knowledge, okay, there are you're stretching that testability factor. You're stretching it. Stretching doesn't mean it's gone completely, but you may not be able to do direct investigations on it. So you have to kind of work around the actual setting up of an experiment and controlling and etc. But you can look at predictions, and then you can look for evidence of those predictions, and see, that's the key. If your theory can predict the future, if it can predict what might happen, and you go and search for data that supports it, then that's not quite as good as being able to test it and generally agree on it, but it might come up with enough that people start thinking, well, maybe it's something we need to look into and find out if we can start testing. Then there's fringe science. These are imprecise. There's little, if any, data. It's not accept. These are not. This fringe science is not accepted by the scientific community. There are many examples of this kind of these kind of ideas that are kind of, again, on the fringe. Not saying they're right or wrong. Just saying that there's no scientific evidence for it. So this kind of wheelhouse of scientists isn't going to be accepting the idea quickly in the realm of science. Okay, and then finally, beyond all this science, beyond the fringe, and there's a lot of fringe science, beyond the fringe science, beyond the frontiers, beyond the core, all the way out here is the stuff that's just not science. All right, so is this stuff somehow less valuable? Is this stuff somehow less, I don't know, is somehow more, is this something that we somehow can just look down upon? No, I don't think that this is you looking down on I don't think this is saying that this belief systems and the stuff that's not science is no good. It's saying that it's not science, and that's just that simple. That this is fine, it's just not science. It's not tested, it's not been shown to be valid, and you can't predict anything with it in any kind of reproducible way. And because of it, it's not science. And that's just that simple. Now, there are people out there that say that makes this somehow less. That's their opinion, but that's not what science is saying. Science is saying that it's just simply not part of this kind of thinking, and therefore not something that we could really talk about. All right. So models are where we start to construct these theories and hypotheses, and we'll call them theories at some point. We take these theories and you start looking at one aspect or another of it. All right. So you take a theory and you define it in some way. So the theory that the Earth is round. So you take and you, instead of flat. So you would take and you would make, you'd make a globe, right? If the Earth is round, you should be able to make a globe, and the globe should have, land masses, and it should show islands, and it should have, you'd have a globe, and that globe, would maybe even spin to show the how the Earth spins around around its axes, and the axes might be have the proper angle actually as well. So all this might be accurate, very good. And then, well, how does that help us? It helps us understand what the implications are of having a spherical Earth, and meaning that because the Earth is spherical, because the Earth spins, the sun, the day is 24 hours. There are implications. There are consequences to the fact that the Earth is round and it spins. The fact that it spins, it causes what's called the Coriolis effect, or the spinning bends positions. So if you wanted to go from here to here, you could not go in a straight line, as we discussed earlier, not just because the Earth is curved, but because the Earth is moving underneath you. And so there's all kinds of things that are influenced by just a simple idea that the Earth is round, and this idea, though, can be understood better if you make this model. And a model could be some physical representation, but it could be just some formulas. E equals mc squared is a model. It's a model on a concept, and you can test that model. You can test that theory, and then it's looking at the relationship between three different aspects. The cell is a model. When you draw a cell and nucleus, it's not the actual thing. This is not actually energy going into mass and the speed of light, taking mass the speed of light squared and making energy. This is not an actual cell. It's just a drawing of a cell, but it represents the cell. It represents everything we know about the cell. It's theory taken and put into a diagram or a three-dimensional object. Okay, so these are ideas, scientific ideas that are made to come to life, and these are what we call models. They don't encompass all ideas. They only encompass the ideas that are in the model. All right, so the globe doesn't talk about the tectonic plates. You can't see the plates moving. There's no heat source in the center of this globe. There's no molten lava that if you puncture a hole in it, molten lava won't come out. This model is not perfect. All right, I don't know of any perfect model, but this model is a model that just is looking at a couple aspects of the Earth. It is not a complete, it's not a complete replica of the Earth in miniature. It just is talking about rotation, general position, and the general shape. Where here in the model of the cell, it talks about location, position, general structures, but nowhere in this model do you see things moving across the membrane, DNA being turned into protein, etc. This particular model, this cell model, is just looking only at kind of position and general orientation for the cell. All right, so I hope they get the idea of what a model is. It looks at a kind of a very, 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 very simple. It's a simplified construct. All right, so it's looking at a very limited range of characteristics of a particular theory. All right, so uncertainty, that error that we talked about earlier, it's important to understand what that error is. And so you look at, a lot of people put a lot of faith in how scientific measurements. I hate using the word faith with science because they're almost polar opposites. We have faith in things, even if you don't believe in a higher power. Faith is something we do every day. We have faith that our system works, so when we cross a bridge, we kind of hope we have this faith or hope that when we cross it, it's not going to collapse because somebody messed up. We have faith in I don't know, that the police officer with a weapon is going to shoot you, is going to go crazy and shoot you and your children while you're walking the street, that is that, and we have that faith, even though it's been tested on a number of occasions. Bridges have fallen, police officers have gone rogue, but the bottom line is that faith continues, because if you didn't have faith, you wouldn't cross a bridge. And if you didn't have faith in that police officer, you wouldn't go near him especially if you see the weapon. So there is a level of faith that goes on every day, but people put that faith sometimes in scientific measurements. People put more faith in scientific measurements and scientific theories and than the scientists do. And I think I believe that the reason that this is the case is because of the amazing things that science has been able to accomplish. The this idea of being able to reduce deaths by infectious disease, the surgeries that we've been able to do, being able to do these amazing things with electronics, our video games, etc. These things have shown the science has led to and can lead to some amazing feats of comfort for us. Air conditioning. I'm sitting in an air conditioned room on a hot, humid day. That would have been a miracle for someone when it first came out. Cars, planes, boats that just boggle the mind at how we're able to do the things we do, and people just assume that these miracles, they call them, I think a lot of times people call them miracles, that means science knows what they're talking about, and so therefore they know what they're talking about, therefore that's it. If a scientist says it or measures it, then it must be true, it must be accurate. And that's why people are so shocked when there's when scientists come out and say, well, this is now the new theory, and then people respond to that in a negative way, and they start to lose that faith that they really shouldn't have had to begin with. It really is not. It shouldn't be about faith here. It should just be, this is the concept we have right now. We're not certain about anything. We never have 100% certainty in science. There's always a level of uncertainty, and that's because we're constantly measuring things, and we're uncertain about our measurements. And then just because we measure things, as I said in class, most of the matter and energy in the universe is not detectable by us. So everything we do in science is just what works now. Every experiment leads to a body of knowledge, and that body of knowledge, all of it is uncertain to some degree or another. But that doesn't mean that we don't go with it. That doesn't mean you don't cross the bridge. That doesn't mean that you run away from a police officer screaming. That means that you don't have to have faith in it, but you do have to have this kind of concept that, well, it's the best thing we got right now. This is the best knowledge we have right now, and hopefully it doesn't negatively impact me, that I'm going to go with it and use it as if the premise are correct, and make my deductive reasoning and make my choices as best I can. A scientist is trained to expect error in measurement, okay? In fact, without knowing the uncertainty of a measurement, the information is virtually useless. So when we look at any kind of measurement, when we look at any kind of data that we collect, all right, we accept that there's some kind of plus or minus. And you'll see this on your devices. There's always a plus or minus. This is, not always on devices in the general public, but if you're going to go and measure on a balance, there's going to be, you weigh something, it says 100 grams. It's 100 grams plus or minus something. When you measure temperature, you can take a thermometer, you can measure something 100 times. You won't always get the same temperature. And even though it is the same temperature, even though the temperature hasn't changed, you'll get the device measuring different temperatures throughout that 100. It'll just be a plus or minus. There'll be some level of error in how we read the devices or how the device works. because nothing acts consistently in our universe, and our devices don't measure the universe consistently. So there's no way for us to be consistent uh, in in the data that we collect. But we can identify a range. So we can identify a range. Let's take a look at what I mean by that. So an example of this is if we were an engineer and we were tasked with discovering the temperature of a connector that would fail, and after many tests, the experiments, you discovered that the connector would fail at 1 degree Celsius, right? Would you? So if you got a 1 degree Celsius, just 1 degree above freezing, that connector would fail, and the plane would crash. Would you fly on a plane whose wings were connected by one of these connectors if the temperature were 0 degrees? Right, right. So if it got above 1 degree, the connector would fail and the plane would fall. Right. So now you're measuring the temperature and it says 0 degrees. Would you fly in that plane? We'll talk more about this in class, but just know, ask yourself, what would happen if, yeah, what would happen? And when you're asking yourself if you would fly or not, when you're answering this question, think about this idea of uncertainty, the uncertainty of measurements, and then you're measuring the temperature. So remember, if it's above 1 degree, or rather, if it's above 1 degree, it's going to fail, and you're measuring it at 0 degrees. Kind of three big pieces of error that you have to consider, and that's first is experimental error. So that's the errors that happen while you're doing the experiment. They are random, right? And you can't really predict them, but there'll be things like someone doesn't read two people read the triple beam balance differently. You read the temperature differently. So there's several sources of error. Experimental error is being one of the more common ones. Then there's a systematic error. So there's error in the machine itself. So this is different people making various random errors or in measuring. And here in systematic error, the machine itself has something wrong with it. There's some kind of calibration issue. So instead of reading 100 grams, it reads 20 grams lighter than what it is all the time. So because of some error in the programming or error in the device itself. So then this systematic error is actually sometimes easier to discover than not. And I guess sometimes harder too. It depends on what kind of systematic error you have. But systematic error is also a type of error that you should become familiar with. And accuracy, precision are all important for work in science, and you should know by now what accuracy and precision are. But accuracy is when you can hit the bullseye, okay? When you hit that bullseye, as I said in class, when you hit that bullseye with the arrow, all right? When you're looking at that bullseye and you hit it with the arrow, you're very, very accurate. But if you hit it every time, when we're talking about precision, so this is accuracy. You get to the truth. You're at the center. You're making accurate measurements. You're getting the right answer. This in science is not easy to get, and in fact, 99. We assume that we're not going to be accurate. It's a matter of how accurate. All right, you're not going to get 100% accuracy. The question is, how accurate are you? Right, and I know that there's a lot of people that are competitive that would sit there and argue that, but the bottom line is you're not going to get to the accurate answer because of all the things and unknowns that we've discussed up to this point. And when you're precise, however, precision is something that you can get to. You can get to this thing called precision, and that's it every time I hit. So I might hit one there, but then every time I hit the target, it's in a very tight group. Now which one of these is more precise? The one that well, I should say, maybe I'll make two different symbols. So So this one, the triangles or the x's, which one's more precise? Well, hopefully you say the x's, because the x's have a tighter grouping. So by if every time I measure, I'm not near. You see how over here I'm over here. Let's say this group is, I don't know, 20% off the center, right? So they're away from the center, 20%. But they're all together. I'm always getting the same 20% off error. Where here in the triangles, I actually almost hit the target. I'm almost there. You see that one really great measurement. But then I look at the other measurements and they're really far off. And I can't tell how close or far away I am from the center. So because I can't tell, this is actually worse precision. This unknown is not, I can't define it. But because this 20% is defined, this is 20% error, right? But I know it's 20%, so every time I measure it's going to be 20% off. I can make some much better predictions using this information. So precision versus accuracy. It's important to have both. You want to be as accurate as you can, but there are serious limitations to accuracy. Precision is something we can achieve and something we can continue to strive for and come very close to 100% on. You can always be as precise as is possible, and it's a goal that I think is much more attainable. Okay, so here's a good example of not having our pluses and minuses, uh, and because we don't have an error estimation, we were given some false information. And these are previous estimates, previous studies that people have done, and they came up with these numbers. And who knows who actually said it? Actually, they're all listed here if you want to look them up. But in this study, they discovered that a lot of people were making bad decisions based on bad premises. And the bad premise was that if we plant enough trees, we can compensate for carbon dioxide emissions in the atmosphere. Well, the reason that's a bad premise is that all the information about how much biomass is in trees and then how much carbon they could actually take out, biomass in trees is here and carbon they can take out is here. Previous estimates were fairly high, really big, very big numbers, but there's no estimation of error. Where if we look at the biomass of 4.2, that's the actual number that this study came up with, and they said we have an error rate of about 1.0, plus or minus 1. So this could be as high as 5.2, right? Or as low as 3.2. And that's because that's what that plus or minus means. And if we take a look at how much carbon is trapped in that biomass, we're only looking at 1.9, not anywhere near the 7 that you see here, or even the 6 here. At one point, in fact, the closest one seems to be this study here. But if we take a look at 1.9 plus or minus 0.4, we're looking at something that can be as high as 2.3 or as low as 1.5. And I know that's the confidence level of that this study has given their results. And now you know that you're at 1.3 at something along the lines of 2.3 to 1.5 kilograms per meter squared, and that's just not enough to make an impact on the carbon emissions that we're putting into the air. If we take a look at metric tons, how many metric tons does that mean? The total biomass of the boreal forest is 22 metric tons. 22 times 10 to the ninth metric tons plus or minus 5. So it's 22 plus or minus 5. So it can be as high as 27 or as low as 17. So it can be as low as 17 or as high as 27. That would be the total biomass. Now look at the numbers that they gave. The lowest number that the previous studies had given is 30, and here they're saying the highest you could possibly get is 27, and the lowest is 17, and there's nothing even come close to the low range here. So there's a real miscommunication here. There's a real overestimation about how much carbon trees can take out of the atmosphere. And if you take a 9.7 here plus or minus 2, okay, now you're wondering, wow, that's a real big difference from what the previous estimates were. And you're wondering, how did this possibly happen? And you're wondering if it was actually a mistake that they didn't put the error rate, or was it almost on purpose? So there's a lot of stuff that you got to start thinking about when you're looking at data that doesn't report error. Now there's something we should mention about science. One last thing. I know this has been a long video, and hopefully you haven't tried to watch the whole thing all the way through. But you have some ways of looking at historical evidence, at stuff that's happened that chronicles events, in some cases over millions of years, without actually having to do controlled experiments. And so in a case, well, that's not true. You still do controlled experiments, but the source of a lot of your data is going to be this ancient treasure trove of data that you'll find in glaciers, underneath preserved woods, even in forests themselves. This tree was cut down, and in this area, this part you see here, this is evidence of how often this forest where this tree was cut down was burnt, because this tree had survived many events, forest fires. And this professor that looked at the data from this forest, and they had cut down trees or had found some logging that was going on, and they looked at tree rings. You'll notice that the tree ring shows damage, and you should know, and by this point I think everyone knows, that the distance between tree rings is defined as a year, because this was the growth year. The tree takes this is the amount of wood that the tree grew in a year. And so you can go back many years in this case and see that every year there was a fire, or not every year, but every so often there was a fire. And that fire, that forest fire, is a natural event. This wood in here did not get burned by a recent fire. This was burnt a long time ago. So this data is in the trees. The data is in the rocks. This data is in the amount of in gas pockets found in ice that have been buried for millions of years. We can gather this data and analyze it and do experiments with it and compare it to controlled experiments, where we compare them to other trees, or more, for in this case, other trees more recently grown in places where there are no fires, and you can compare and make conclusions based on hypotheses. So you can use your deductive and inductive reasoning, but it's just that your historical evidence can be a very important alternative to direct experimentation. And I'm not so sure it's an alternative as much as it is. It's a piece of information, and you might want to go ahead and do some other experiments. For instance, in this case, you want to grow a small forest in a controlled environment and expose it to a fire, and and then douse the fire out quickly and see what the results were or are to the tree that didn't burn down but was exposed to fire. Let it grow for a year or two, and then cut it down and see if you have the same type of structures. So this structure, what are we looking at? Well, there's suppositions, but maybe in addition to looking at historical evidence, you add some experimental evidence to help support your concept. And of course, modern catastrophes are really an important source of data as well. Whenever there's earthquakes and there's damage done, or we see the San Andreas Fault separate another 3 centimeters this year, or you see some big event happening you can go back and you can say, okay, this happened. Our models predicted this. This is what happened. What was the result of after it happened? Our model suggests that it's going to take years and years and years for this to recover, this area to recover, but it actually only took a couple years to recover. What's going on? So this is actually yet another example of how we can test we can't create earthquakes, we can't create volcanic eruptions, but we can collect data, take down notes in areas where this does happen, and then compare our theories and our models to the event and see what part of it worked and what part of it didn't, and go back and reconstruct and follow that whole flow chart that we talked about earlier. Well, I hope this helped. I think that a lot of this information is something that you can understand, that you can do well. You're going to have to apply them. It's only going to be 15 questions on Monday on this whole PowerPoint. So try to hit the most important parts. Discovering what the most important parts is one of the difficult things you'll have to do this year. Try to focus on the things that I kept repeating. For example, I think I repeated disprovable or disprovability many, many times. The scientific method, I think I repeated myself many, many times throughout this video and in class. Those are going to be the sources of most of your questions. Understanding the concepts, trying to apply them. To summarize, I would say, first off, I would make sure that I knew the difference between everyday thinking and scientific thinking. All right, and in the type of question I'm going to ask you is, I'm going to have a passage, and you're going to have to identify where is the is it common, is it everyday, or is it scientific, and you're going to have to collect evidence. You're going to have to support it. You have to support your statement with evidence from the passage. So what's going on in the passage, and then write down, I think this is everyday thinking because. All right, so that's one. Two, I think I think it's a really key idea that you understand that. Oh, by the way, I would definitely remember disprovable. I would definitely know what independent variable is. I would know what dependent variable is. For the quiz, I would know, if I were you, why that we need to control all the factors uh, in an experiment. And change only what this triangle means change only one thing at a time. That's kind of an amazing principle that really is underestimated how important it is for a lot of kids. For know what a control group is, both positive and negative controls. So know what those are. 5, know how How is error an important issue in thinking? How do we deal with it? How do you deal with error? And here we're talking about measuring it, defining it, and then anything that we say within a certain range of error, and we have reasons why we say it. We don't just make a guess at saying plus or minus 5, as in the chart that you just saw. And the chart that you just saw is an example of the kind of use and how we deal with error. All right. So you have to deal with it. You just can't assume it's there and just keep going. Which is what crop circle people say. They ignore the error, or they just go ahead and stay ambiguous. The idea of reproducibility. Right? Can you reproduce these results? If I do the same thing you do, I should be able to reproduce those results. I should get the same results. If I don't, there's an issue. And lastly, what are the outside of experimental evidence of actually experimenting with things? What are some sources, some other sources of scientific thinking? Remember that we can't experiment with earthquakes or volcanic eruptions, but we can measure, and we can account for error, and we can look backwards instead of forwards. So we can see if our predictions for our theory actually happened by looking at what happened and comparing it to our predictions. All right, so in any case, that is what the quiz is mostly going to be about. You're going to have passages. You're going to have a passage. You're going to have a short answer component where you're going to have to read the passage. Remember, most of your quiz is on Tuesday. The upperclassmen, your quiz is on Monday. Good luck.